Have you ever wondered why particles behave so mysteriously in the quantum world? Well, you're not alone. Quantum physics, a realm of science that deals with the tiniest particles in the universe, is a world full of paradoxes and intriguing phenomena that challenge our understanding of reality. The wave-particle duality, for instance, is a cornerstone of quantum physics. It's a concept that particles can exhibit characteristics of both waves and particles. Sounds a bit mind-boggling, doesn't it? Yet it's been proven time and time again in experiments. And then, there's the famous double-slit experiment. This experiment demonstrates that particles can act as both particles and waves. When we're not looking, particles act like waves and go through two slits at once. But when we observe them, they act like particles and go through one slit. This experiment sets the stage for the weird and wonderful world of quantum physics. And trust me, we're just getting started. Ever heard of two particles being connected no matter the distance between them? It might sound like science fiction, but it's a fundamental aspect of quantum physics called entanglement. But how do we know this phenomenon is real? Enter Bell's theorem. John Bell, a physicist from Northern Ireland, proposed a theorem in the mid-20th century that offered a way to test whether particles really do affect each other instantaneously across great distances. His theorem revolves around the concept of hidden variables, factors that, if they existed, could explain quantum behavior in a way that aligns with our everyday experiences. Bell proposed a test, now known as Bell's inequality, to determine whether these hidden variables exist. If the inequality was violated in an experiment, it would confirm that these hidden variables don't exist, and quantum entanglement is indeed a real phenomenon. Experiments have since been conducted, and they've shown that Bell's inequality is violated, backing the concept of quantum entanglement. These experiments, known as Bell test experiments, have played a pivotal role in proving the veracity of quantum physics. So what does this mean? It means that particles can indeed remain connected across vast distances, affecting each other's properties instantly. It's a concept that defies our everyday understanding of the world, showing us that the quantum realm operates under rules vastly different from our macroscopic world. Entanglement, a cornerstone of quantum physics, defies our everyday understanding of the world. How do we know quantum physics is real? This question has puzzled scientists and laymen alike for over a century. The answer lies in the groundbreaking quantum experiments that have been carried out over the years. Let's start with quantum superposition. This is the idea that a quantum particle can exist in multiple states at once. It's like flipping a coin, where the coin is both heads and tails at the same time, until you look at it. The famous Schrödinger's cat thought experiment encapsulates this concept, where a cat in a box is both alive and dead until observed. But how do we prove such a counterintuitive idea? Well, experiments with particles of light, known as photons, have shown exactly this. In one experiment, a single photon is sent into a beam splitter, creating a state where the photon is in a superposition of going both left and right at the same time. Next, we have quantum tunneling. This is the phenomenon where a quantum particle can pass through a barrier that would be insurmountable in the classical world. It's like throwing a ball at a wall and finding the ball suddenly appearing on the other side. Experiments with electron microscopes have shown this to be true. When a thin layer of material is placed in front of a source of electrons, the electrons can tunnel through the material and be detected on the other side, even though classical physics would say this is impossible. These experiments, along with many others, provide tangible proof of the quantum realm. They show that quantum physics isn't just a set of abstract theories, but a real and fundamental part of our universe. These experiments are the stepping stones that have led us to the development of technologies like quantum computers, and will continue to guide us as we delve deeper into the quantum world. So the next time someone asks you, how do we know quantum physics is real? You can tell them about these fascinating experiments. These experiments provide tangible proof of the quantum realm. Can quantum physics solve problems faster than classical physics? The answer lies in quantum computing, a fascinating field where quantum physics meets computer science. Quantum computers operate on quantum bits, or qubits, which leverage quantum phenomena to perform complex calculations at mind-boggling speeds. Unlike classical bits that can be either 0 or 1, a qubit can exist in both states simultaneously, thanks to a quantum quirk known as superposition. This means a quantum computer can process a vast number of possibilities all at once, making them exponentially faster and more powerful than their classical counterparts. Entanglement, another quantum phenomenon, allows qubits that are entangled to be linked together in such a way that the state of one qubit immediately influences the state of another, no matter how far apart they are. This unique property offers quantum computers the potential to solve problems that are currently beyond the reach of classical machines. Today, quantum computers are being used to tackle complex issues in fields such as cryptography, material science, and drug discovery. For instance, Google's quantum computer, Sycamore, has reportedly achieved quantum supremacy, performing a calculation in 200 seconds that would take the world's fastest supercomputer thousands of years. Quantum computing, a practical application of quantum physics, revolutionizes the way we process information. It's not just a theory, it's a reality that's transforming our world. Can we teleport information in the quantum world? You might think this is a question straight out of science fiction, but it's a real concept in quantum physics called quantum teleportation. Now, before you start imagining teleporting to work to escape rush hour, let's clarify what it actually means. Quantum teleportation refers to the process of transmitting quantum information from one location to another. This doesn't involve physically transporting anything, but rather transferring the state of a quantum particle. So in essence, we're teleporting information, not matter. This becomes possible due to quantum entanglement, a strange phenomenon where two particles become linked, such that the state of one instantly influences the other, regardless of the distance between them. Using this principle, scientists have successfully teleported quantum information over considerable distances. Quantum teleportation, while still in its infancy, is a fascinating demonstration of quantum principles. It's another piece of the puzzle, further validating the remarkable and often bewildering world of quantum physics. Can quantum physics secure our communication and data processing? Let's dive into the intriguing world of quantum entropy and information theory. Quantum entropy, much like its classical counterpart, is a measure of uncertainty or randomness. However, it's unique in the way it handles this randomness, offering us a new perspective in the realm of information theory. In the world of classical physics, information is processed in bits, the basic units of information. But enter quantum physics, and we meet an exciting player, the quantum bit or qubit. Unlike classical bits, which can be either 0 or 1, a qubit can be both 0 and 1 simultaneously, thanks to the principle of superposition. This allows quantum computers to process a vast amount of information simultaneously, leading to faster computations. But what about security? Here's where quantum entropy really shines. In the quantum world, we can use a principle called quantum entanglement to create pairs of entangled qubits. If anyone tries to intercept the information, the state of the qubits changes, alerting us to the intrusion. This forms the basis of quantum cryptography, a method of secure communication that harnesses the principles of quantum physics. Thus, quantum entropy and information theory are not just abstract concepts. They hold the potential to revolutionize our communication systems and data processing techniques, making them faster and more secure. Quantum entropy, a unique aspect of quantum physics, plays a crucial role in information theory. Is quantum physics confined to the laboratory? Far from it. Quantum physics, the curious science of the very small, has a surprisingly large impact on our everyday lives. Consider our digital world. The silicon chip in your smartphone, the heart of all modern electronics, relies on quantum physics. It's the quantum mechanical nature of electrons that allows semiconductors to function, powering our devices from laptops to gaming consoles. But that's just the beginning. The quantum revolution is reshaping technology. Quantum computers, capable of processing vast amounts of data at unimaginable speeds, promise to unlock new possibilities in fields from medicine to meteorology. Quantum sensors, another emerging technology, could transform everything from navigation to medical imaging. These sensors harness quantum properties to measure physical quantities, like temperature or magnetic fields, with unprecedented precision. And let's not forget about quantum communication. Using quantum entanglement, we can create secure communication channels, immune to eavesdropping. This technology could revolutionize online security, protecting everything from your bank transactions to national security information. So while quantum physics may seem abstract and intangible, its effects are very real and tangible. It's the invisible hand guiding much of our technology and will continue to shape our future. Quantum physics, far from being purely theoretical, is the foundation of our modern world.